hypothalamus secretes GnRH to stimulate the anterior pituitary to secrete LH or FSH, to stimulate the gonads to secrete steroid hormones, which, blah, 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 depending on what the steroid hormone is. So what are the steroid hormones down here? The examples of that would be estrogen, progesterone, and testosterone. So each of those are going to have different effects. So one is going to be for male characteristics, one is going to be for female secondary sex characteristics, or for the development of the gametes, all right? So all of these, what they're gonna do to the various tissues is gonna be different. But that's one way to kind of look at the relationship when you're describing it, that whatever the gland is, or whatever the structure is, it's going to secrete the hormone, and the hormone is going to stimulate another gland in order to release something else. So the first one that we are going to have in the list that we'll talk about is the one that is in the center. This is the thyroid gland. So we'll do thyroid, then we'll do adrenal cortex, and then our adrenal gland, then we're going to do the gonads. Okay, so with the thyroid gland, okay, just know that where it's located, right? This is the largest purely endocrine gland that we have. Purely endocrine, meaning that it is 100% endocrine. It's not one of those that's going to be shared. What's one that's shared? The pancreas is a large gland. However, it's endocrine and exocrine at the same time. The gonads are actually endocrine and exocrine at the same time too. So this is the only one that we have that is purely endocrine, and it's very large. This is going to secrete, of course, thyroid hormone, and this is for increasing metabolism. This is something that we talk about more in lab. The two hormones that it will secrete is thyroid hormone and what's called calcitonin. The thyroid hormone / T3 or T4 is the one that is captured in this image. Calcitonin is not captured in this because it's a different stimulus in order for calcitonin to be released. How many of you kind of remember what calcitonin is? Or what general unit or chapter was it from? What organ system that we were talking about with calcitonin? What was it?
Bones.
Bones. It was the skeletal system. Calcitonin toned calcium down. Does it need the hypothalamus to do that? No, it doesn't. Okay, so what's the stimulus for that? Calcium was too high, and that was pretty much it. That's why it's not included in here. But there are two different cells that are going to secrete the two different things, and that is something that you would do in lab. Now, if we bring our idea of negative feedback and how it's supposed to work, this is how it's supposed to work, ideally, in what's called an axis. It's a signaling interaction between these three, hypothalamus, anterior pituitary, and any one of these three. So what I've described here, what we have listed, this is an example of an axis. So you should know generally what the three axes are, and then the arrangement and how they are related to each other. This is how negative feedback should work if thyroid hormone and this whole system is working the way it should. Hypothalamus releases TRH, cool. Stimulates the anterior pituitary to release TSH. TSH stimulates the thyroid to release T3 or T4 or TH, thyroid hormone. And then it's going to raise the levels of this hormone. We're going to raise metabolism and different parts of that metabolism to a certain point, or set point, like what we did with our thermostat at that 72 degrees. And once we get whatever that characteristic is within that normal range of maintaining homeostasis, having too much of this in the blood is actually going to negatively feedback on the anterior pituitary and negatively feedback on the hypothalamus. Because of that negative feedback, we're going to have less of this secreted, we're going to have less of this secreted, and in essence, this secretion will be shut down. That is how negative feedback is supposed to work. Again, hormones are not going to be released willy-nilly and randomly if the gland feels like it. No, it's always in response to something else. And once we've already ended up in that nice set point, we don't need the hormone anymore. So if this becomes an excess, okay, we can't have it in excess. Having an excess here will actually inhibit. That's what the negative is. So what's the opposite of stimulate? Inhibit. Opposite of stimulate is inhibit. So something positive, it's making it do something. This is when it's stopping it from doing something. So too much of T3 and T4 will inhibit the anterior pituitary, and it will inhibit the hypothalamus, so that now these two are not going to be releasing that hormone. That's the thyroid axis. This is when things go wrong. So hyperthyroidism and hypothyroidism. Hyperthyroidism and hypothyroidism does not have to do with the size of the thyroid. I want to make that very, very clear. Because when you think of thyroid, sometimes you may think, you might have the image of somebody having goiter and having this enlarged thyroid. The size of the thyroid does not make it hyperthyroidism. It's the amount of thyroid hormone that the thyroid gland is actually producing. So if it is regularly producing too much, we call that hyperthyroidism. If it is producing too little, we call that hypothyroidism. And as a disease process, when we're thinking of disease, we're thinking of chronically making too much, chronically making too little, not only temporarily because of negative feedback. So this involves the activity of the gland itself. I'm just only going to talk about a few of them. So first there's Graves' disease. Graves' disease is the most common type of hyperthyroidism, which means that too much thyroid hormone is being produced. How does this happen? Typically, the body, the patient's body actually makes antibodies against their own receptor. And when they make it, there's a couple of things that we can do with an antibody. We can either make that receptor overactive, or we can actually inhibit that receptor entirely. When it comes to Graves' disease, we're actually making it overactive. So abnormal antibodies stimulate the oversecretion of thyroid hormone, and so everything that has to do with an increased metabolism, a chronically increased metabolism, such as the following, is going to happen. Typically nervousness, weight loss, sweating, rapid heart rate. All of these are indicators of having too high of a metabolism from having too much thyroid hormone. So that's hyperthyroidism, that's the example. It's not always going to be Graves' disease, it's just the most common form. Then there's the opposite. If you are not making enough thyroid hormone. There's myxedema, and then there's the one with endemic goiter. Okay, so I'll talk about both of them. Myxedema is adult hypothyroidism. We're not making enough, only this time the antibodies, rather than causing the increased production, okay, but it's actually going to attack the thyroid tissue and decrease the production, which is why it's hypothyroidism. So the levels of TH would be too, what is it? Hypothyroidism is what? Low. TH is hypo. Hypo is under. Too?
Low.
Too low. Okay? So this person would have low metabolic rate. They will typically have weight gain. And going back to this idea without talking super deep into it, this is ideally how things should happen. In the case of myxedema, if your T3, T4, if your TH is much too low, what is the anterior pituitary and the hypothalamus going to think? What do you think is going to happen? What can you tell me about the level of TSH in this patient? If their TH is too low, what is the anterior pituitary going to want to do to compensate for that? What is it going to do with regards to TSH? It's going to increase it to try to compensate. That is a failure in feedback. Okay? Because now, since this is destroyed, your anterior pituitary has no idea that this has been destroyed. Because this is destroyed, this causes this to be low, which is going to, okay, make the anterior pituitary think, oh, there's not enough of that. You know what? I'm going to stimulate the thyroid more. So these would be high, this would be low. Okay? Let's look at goiter. Enlarged thyroid. This is typically due to the lack of iodine in the diet. Now, why is that important? In order to make thyroid hormone, you need iodine to make thyroid hormone. Iodine is something that your body does not make itself. This is something that you have to get externally, which is why in history they have introduced the idea of iodized salt, because people were not getting enough iodine and they weren't able to make enough thyroid hormone. So what do you think is happening? Okay, the thyroid gland is under the control of TSH. TSH is going to keep stimulating the thyroid gland, but the thyroid gland cannot make thyroid hormone because there's no iodine. So what's going to happen? The thyroid is going to enlarge as a result. That's what endemic goiter is. And we say it's endemic because it's typically region specific. That goiter is not something that everybody's going to have in a large area. It usually affects a certain area, a certain geographic area where there is a lack of iodine in the diet. That's why we call it endemic. That means versus pandemic. Endemic means that it's within a certain defined area. Typically, not enough iodine. Okay, this is an example of hypothyroidism. The next one is adrenal glands. The adrenal glands. The adrenal gland is two endocrine glands in one. There is the adrenal gland right here. Here's the kidney. Adrenal means on top of the kidney. And the adrenal gland looks like this. This has it kind of blown up. This is the medulla. And this is the cortex. The cortex gives you steroids. And the medulla gives you epinephrine. So this was one that we had mentioned when we looked at the autonomic nervous system. So make sure that you review that. What that core does, that adrenal medulla releases epinephrine. So we're focused mostly on the cortex part with response to this, okay? Two endocrine glands. So adrenal medulla, sympathetic nervous tissue at the core, adrenal cortex, steroid hormones. These are the steroid hormones that come from there. Cortisol is an example of a steroid hormone that regulates glucose, which is why we call that a glucocorticoid. Aldosterone is an example of a steroid hormone that regulates a mineral. In this case, it's sodium. So that's why we call that a mineralocorticoid. And then we have the sex steroids that generally are called androgens. These can become progesterone, estrogen, and testosterone. Okay? This part here at the bottom, that one I want you to know for lab. So let's focus on just the cortisol part and the cortex part. That's the one that's involved here. That's why I put adrenal cortex and non-adrenal gland, because this is under the purview of ACTH, just the cortical part, not both parts. So we're going to focus on the cortical part. This is in response to ACTH, cortisol, and aldosterone. This is your glucocorticoid, mineralocorticoid, and this is the function of each of those. General terms, you need to know for lab. You need to know generally those functions. That's our adrenal cortex. And just like we had a problem with the thyroid, let's talk about some problems with the adrenal cortex. The adrenal cortex, the two that I would like you to be familiar with, Cushing syndrome and Addison's disease. This is Cushing syndrome. They tend to have what's called a buffalo hump. This is an abnormal deposition of fat that's typically going to be in the upper back or behind the neck. So we'll talk about why that happens. Addison's disease, this has several symptoms associated with it. I don't want you to know all of the symptoms. What I want you to know is one is an issue with hypersecretion, the other one is a problem with hyposecretion. So again, hypersecretion is when you're making too much. Hyposecretion, you're not making enough. So let's look. Cushing syndrome. Hypersecretion of glucocorticoid hormones. This is usually due to some kind of a pituitary tumor or an adrenal tumor. Okay, we're making too much cortisol. One of the things that cortisol will do, cortisol allows for fat to be mobilized. So what does that mean? Fat being mobilized means that we're taking it from the adipose tissue and we're making it readily available as fat. However, if you when you try to redeposit those fat stores, they don't go into the traditional areas of adipose. They end up clustering in different parts and redepositing in other places. And one of those places is going to be the back of the neck, which is why there is what's called the buffalo hump in the back as a marker of Cushing's syndrome, because the fat has been mobilized, but they've been redeposited in another place, which happens to be here. Because it's hypersecretion, let's go back to this idea. We are making too much cortisol. Let's say because there is some kind of a pituitary tumor up there, which causes more of the cortisol to be released. If you have the cortisol, too much cortisol, what should happen? Okay, ACTH should be decreased as a result of too much. Okay, let's say rather than making it a pituitary tumor, let's just say that it's an adrenal tumor instead that is causing too much of this. Let's say the adrenal tumor exists in the adrenal cortex. We are making too much cortisol. Again, what's going to happen to ACTH if you have too much of the cortisol? This should be able to tell the anterior pituitary to lower the ACTH. But does it matter? It doesn't matter, because this is going to be overproducing anyway, whether ACTH is there or not. So they're going to have a high cortisol still, and they're going to have a consistently low ACTH. Okay? So, that's Cushing's. Let's look at Addison's. Addison's is the opposite of that one. Okay? This is going to cause a hyposecretion of both types of the hormone by the cortex. So aldosterone increased. As a result of Addison's, what are we going to notice? If these are too low, what do you expect to find in a patient with Addison's when it comes to their ACTH? This is already too low. So what is the pituitary gland going to want to do? Increase, make more. But does it matter how much it makes? This is destroyed. It's still going to be consistent. What could eventually happen is that this is going to be secreting so much more that it's going to end up getting destroyed itself. Okay? So that's Addison's. Cushing's and Addison's, know them as hyper and hyposecretion. The last one are going to be the gonads. The gonads. These are going to be producing gametes and steroid hormones. It's one of those exocrine and endocrine at the same time. I'm not going to talk about this part because this is going to be reserved for lab with the gonads. Review your other endocrine glands if they look familiar to you. Pineal gland, make sure you know what melatonin does. The thymus, which we saw in the immune system earlier, it has another role in the endocrine system, and that is mainly, it's going to secrete a hormone called thymosin. Thymosin is one of 3 hormones that's going to be used for T-cell maturation to allow for those T-cells to gain a communal competence. Parathyroid gland releases parathyroid hormone. This one I want you to really pay attention to. The reason why, the parathyroid gland is not the thyroid. Okay, that's the most common mix-up that happens. Why? Because this is the thyroid gland. That is the thyroid gland. Parathyroid gland are these. There's 4 little ones that are embedded in the thyroid gland. They are not the thyroid gland. They have a different histology, entirely different histology, and they secrete parathyroid hormone, not involved in this, parathyroid hormone. Does the opposite of calcitonin. So that has to do with calcium regulation. This one's going to raise that calcium instead. The heart, if you did not know, which you might not know, just a little factoid. The heart also has an endocrine function. So there are some organs that have these unexpected endocrine functions, and that is because it produces something called atrial natriuretic peptide. All you need to know, the NAT part. Sodium. Urinate. Pee out salt. That's one you remember, okay? So what does that mean? Natriuretic peptide, this is for sodium excretion. There is reabsorption and then there's excretion. Excretion means you're getting rid of it. Absorption means that you're keeping it. So this one you're not keeping the sodium. What is this for? Why do you want to get rid of it? This is one of the ways that we can lower blood pressure. That's why. That is the endocrine hormone of the heart. Okay. And the last one's here. Almost done. Okay, that wasn't so bad. I'm gonna go erase this one. The pancreas. Okay. I said the pancreas, you're going to see it twice. Endocrine focuses just on these little clusters. Digestive exocrine, that's all of that. That's the 90%. So Thursday, folks, you'll get to see both of them today. Endocrine and exocrine. So look at the endocrine part, 10%. We have what are called these little clusters called pancreatic islets, and then they have two main cells. There's a third cell called the delta cell, beta, alpha, and delta. Let's lower our blood sugar. Let's raise our blood sugar. So they both regulate blood glucose. This one slows down digestion. I will mention that again in lab. The last thing here is the idea of diabetes mellitus. Okay, diabetes mellitus. So there's different types of diabetes. Diabetes is just the general term for frequency of urination. Okay, so urinating too frequently, a lot of water loss. Okay, that's a general term. When somebody has diabetes, most of the time though, when they say they have diabetes, they have this type of diabetes. Diabetes mellitus. There's another diabetes called diabetes insipidus. That one does not have to do with blood sugar, so not all diabetes have to do with blood sugar. Diabetes insipidus more has something to do with ADH vasopressin. That's a completely different thing. But diabetes mellitus, you have two varieties of diabetes mellitus. What are the two varieties of diabetes mellitus? Type 1 and type 2. So I'm going to put DM, type 1, and DM type 2. Of the two, how many of you know which one is considered insulin dependent? It's type 1. So the mechanism behind this, I do want you to know the mechanism behind this is why. In order for any endocrine hormone to work, like insulin, you need to have two parts. You need to have a functioning gland. This is important as that. You need to have a functioning receptor. If either one of those is not functioning, there is a failure in communication. Type 1 to be insulin dependent means that there's a problem with the gland. The pancreas is not secreting enough insulin. Our target receptors are fine. It's just that our pancreas is not making enough insulin. This is also known as juvenile onset. This is the one that is insulin dependent. The more common one of the two though is type 2. Type 2, your pancreas is making enough insulin, but what's the problem? What's the other element here that has to work? The receptor has to work. So your pancreas is making insulin fine, but your target cells are not responding to the insulin correctly. So it's as if that signal is being ignored. This is the one that is typically adult onset. This is usually the one that is associated with some kind of lifestyle factors, okay, and a whole myriad of other issues that are all tied in together. High blood pressure, increased weight gain, okay, all of those, all right, are all involved in that type 2 diabetes mellitus. If it is not treated, what do you think is going to happen to the pancreas? So the targets are ignoring the signal, right? They're ignoring the insulin. The pancreas is going to get tired. So what do you think may happen if you started with type 2 diabetes mellitus? If it is untreated and unchecked, you could actually move into type 1 because your pancreas will get so tired of releasing insulin that it itself ends up getting destroyed. and then you become insulin dependent. Does that make sense? And last thing here is just kind of a fun fact, where the term diabetes mellitus comes from. The term mellitus is from the term for honey. It's an old Greek term for honey. Okay. Oh, it's worse than that. Okay, imagine if you were a Greek nursing student long time ago before there were any kind of dipsticks or urinalysis technology that we have. Okay, what was one of the ways to determine whether a person had too much glucose in their urine?
They tasted.
They were gonna taste it, and if it tasted sweet, there was too much glucose in their urine. They had diabetes mellitus. Glucose, you're like, oh my gosh, oh. Okay, glucose is one of those molecules that's never supposed to end up in the urine in an appreciable amount. Glucose is one of those that you want to keep as a fuel. So your kidney should be able to hold that glucose and then put it back into the blood. If there is too much glucose already in the blood, well then the kidney's not going to be able to put the glucose all back in the blood. It gets excreted into urine. Hence, this is how the glucose ends up in the urine. We all learned something new today. We learned a whole bunch of funny things new. So I would do, this is what my approach would be. For endocrine, keep that somewhere. Know that really well because a lot of it is captured in there and understanding what this is. And then we just need to add the other hormones. And that's it, okay? So Thursday, folks, I will see you soon. Those are my Tuesday. In fact, Thursday and Tuesday, just in general, these last labs, you are free to repeat labs if you want. If it means that, okay, I want to have extra exposure looking at the models again, you are welcome to either of them. We should have enough for you to accommodate